His honors undergraduate thesis. Dan's been working with me for a year and a half now, and he worked very closely with my former postdoc, Chris Herdman, when he was here. Dan's done some pretty interesting and very novel work that we're basically in the process of writing up, where he's essentially one of the first people to ever compute mode entanglement, which he'll tell you more about what that is. Basically the entanglement between the condensate and the particles kicked out of the condensate in a particularly interesting, exactly solvable model known as the Lieb-Liniger Model. And experimentalists, specifically those down at Penn State and State College, can actually make these Lieb-Liniger models in the lab. So it's a pretty, I think it's a really beautiful kind of connection between what is the state of the art in experiment and what's the state of the art in theory for exactly solvable models. So I'll let Dan tell you the rest. And then we'll do the usual questions from the audience, and then the committee will stay to ask Dan a few more questions.
All right, thank you all for coming today. Thanks for the introduction. Before I get started, I'd just like to thank committee members, Professor Adrian Del Maestro, Professor Dennis Clougherty, Professor Charles Toba, and thank you all for being here today. So, my project is called Mode Entanglement in the Lieb-Liniger Model. So I'd like to just jump right in and just talk briefly about what quantum entanglement is. So entanglement is a purely quantum mechanical phenomenon. There's no classical counterpart to quantum entanglement. And in a quantum entangled system, measurements on components of that system are found to be correlated, which is very counterintuitive, especially with the classical case where the components contain the entire information of the system as a whole, whereas in the quantum case, information is actually contained within the system itself as a whole. So in a classical system, for a simple example, imagine you have two coins, maybe heads or tails, and you flip each coin individually, you find what you expect, you get 50% of the time. You get heads the other time, the other 50% you measure tails. And for individual spins, you can make a table, 50% and 50% for each particle. And if you measure the joint outcomes, you find, again, what you expected. 25% of the time you flip heads, 25% heads, tails, and so on. So you could have just as easily pieced together the joint outcome probabilities from the individual outcomes. But that's not the case in a quantum entangled system. And we'll talk a bit more about that in a second. So why is this important? Well, quantum entanglement is necessary. It's a necessary resource in quantum computation. So in order to have a functioning quantum computer, we need to be able to manipulate these robust entangled quantum states. So quantum computers are very important because they can offer an exponential speed up over classical computers. Furthermore, in one-dimensional systems, they generally display more quantum behavior than, say, higher-dimensional systems, 3D systems. And they're also amenable to mathematical methods such as the Lieb-Liniger theory, which predicts this novel state of matter that exists only in one dimension. Furthermore, so the Lieb-Liniger model, as Adrian said before, has seen experimental realization, and that's the model that I've been studying in my research. Just as a simple mathematical example to motivate the theory behind entanglement, suppose we have a two-state, two-particle system that's described by this cat here. So 1 and 2 label subsystems A and B respectively, and 1 and 2 represent the bases of the subsystems. So what we can do, we can associate a density matrix to the state, which after we expand the terms just uses this. And also notice that this composite state, composite meaning two spins, is a pure quantum state at t equals 0 to 0 temperature. This is because there's no thermal mixing of the state at 0 temperature. It's guaranteed to exist in, say, ground state. But, however, the components of a pure quantum state may be in a mixed ensemble. So we want a way of referring to only a particular subsystem, say subsystem A. And to do that, we can trace the density matrix rho over the degrees of freedom in subsystem B. So explicitly, we just compute the sum here. where I labels basis states of subsystem B. And now once we've traced over the degrees of freedom, the reduced density matrix refers only to subsystem A. So colloquially, we can trace out the degrees of freedom in subsystem B to obtain this matrix. And for the state described in the previous slide, we just get this here. And also notice that this is a mixed ensemble, meaning there's some sort of information shared between the components of this state. So the reduced density matrix encodes the amount of entanglements between subsystems. So entanglement also means information shared between these two subsystems. So in order to quantify this entanglement, we use what's known as the entanglement entropy. In particular, we have the von Neumann entropy, which is basically a measure of the amount of this hidden information that is not accessible in classical systems. And so we compute the von Neumann entropy by computing this here, taking the trace of rho A log rho A. And for the state above, we just get this here. And also there's a maximally entangled state, which is also known as a Bell state, when alpha and beta are equal to 1 over root 2. And the maximum entanglement entropy of the state is just log 2. And in general, if your subsystem has a Hilbert space dimension of D, the maximum entanglement would be log D. So in order to discuss and quantify entanglement, we first have to define what is actually entangled. So what the entanglement actually is. So it could be, well, entanglement between regions in space. So imagine we take a region of space and divide it into smaller pieces. We can study entanglements between those regions in space. It could be particles, like spins on a lattice, like in the previous example, for instance. Or it could be momentum modes. So the condensate, which is the zero momentum mode, and the depletion, which is all the other modes. So it can be entanglement between those two subsystems. So a meaningful description of entanglement requires defining a bipartition. So we divide whatever our system is into two subsystems. And then under this bipartition, we can compute the reduced density matrix. And from that, we can get the von Neumann entropy, which is the measure of the information shared between these two states. So the model I've been studying is called the Lieb-Liniger model. It's a system of one-dimensional bosons on a ring of circumference L. And the interaction is a delta function interaction, so it's a contact interaction, and it's repulsive. So it's described by this Hamiltonian here. This is just the kinetic piece, and this is the interaction term. So G is just a parameter that describes the interaction strength. And in the limit, as G approaches infinity, we get what's known as a atomic spheroidal gas, which has some interesting properties that I didn't get to look at yet in this project, but it sort of mimics a fermionic system, because in this infinite repulsion limit, by the Pauli exclusion principle, these particles can occupy the same quantum states. So even though we have a system of bosons, it kind of acts like a fermionic system. So the method I use, well, we want to compute these interesting quantities such as entanglement entropy. It's a quantity called the condensate fraction in the ground state of the Hamiltonian at t equals 0. So what we usually do, we solve the Schrodinger equation here for the ground state. But unfortunately, it's not that simple. So what Lieb and Liniger proposed was what's known as a beta Ansatz solution, which is just kind of a result of using physical intuition as well as the Schrodinger equation and periodic boundary conditions. So it's essentially just the sum of plane waves, essentially, and these coefficients are fixed by the physics. So the beta Ansatz computes energies and eigenfunctions, but after that you're kind of stuck, because in order to compute expectation values, you have to do high-dimensional integrals, so integrate over all particle degrees of freedom. So we're basically limited to the energies of wave functions, so we need a new approach, and the approach that I use here is called exact diagonalization, in which we compute energies and eigenstates by directly diagonalizing the Hamiltonian. So there are drawbacks, namely the that the matrices we study grow very rapidly with system size. So we're limited by just the physical computer memory we have. But with this method, you can calculate quantities that are generally very difficult to calculate by any other means. So there are definitely benefits to this method. So the Hamiltonian before has a matrix representation. So we can choose to represent this matrix with respect to a particular basis. And we can choose in particular the set of non-interacting eigenstates. So if we set G equal to 0 previously, we just get this kinetic term, which has an exact solution. And so the eigenstates of this non-interacting basis are labeled by this integer m, which represents basically the momentum of the eigenstate. And it's just an integer that can take on any integer value. So there are two ways of labeling these eigenstates. The first way is the first quantized notation, in which we label the modes of each particle individually. So this would be the momentum mode occupied by the first particle, second particle, third, and so on. But we also have this second quantized notation here, which enumerates the occupancy, the modal occupancies. So especially for larger system sizes, this becomes very useful because we can compactly represent these states here. Right, so Hamiltonian has a second quantized form, so I won't go into the details on how we arrive at this form here, but in second quantized notation, we just have the sum of the kinetic term, and then this interaction term here. So these are the creation and annihilation operators, which have well-defined effects on these occupation states. So now we can compute these matrix elements directly and construct the full Hamiltonian element by element. So one problem that arises here is that since the non-interacting eigenstates can take on any mode essentially, and is not restricted, so the Hilbert space dimension is infinite. So in order to do numerical approximations, we have to truncate this Hilbert space by introducing a mode cutoff, after which occupancies are zero. So when we do this, the dimension is given by this factor here, which isn't infinite, but still grows very rapidly in both the system size and this cutoff. So once we've done that, once we do this, we introduce an error, but it's a reasonable approximation in the weakly interacting limit, because particles are less likely to occupy higher momentum modes. So now we can, once we've built this matrix, we can diagonalize it through numerical methods such as the Lanchos algorithm. Unfortunately, these matrices require a lot of memory, as well as the Lanchos algorithm, so we're limited to smaller system sizes and cutoffs. But once we do this, we obtain the eigenstates here as linear combinations of these occupancy series. So it's this form of eigenstates that allows us to calculate these important quantities such as entanglement entropes and constant fractions, and that's pretty unique to selective randomization. Right, so following the steps that I mentioned before, we first define our bipartition. So the bipartition we chose is this condensate, which is the n equals 0 mode, and the depletion, which is all the other modes. And we can represent our occupancy states by just a product of condensate and the depletion. So then we can construct our density matrix, which is just this product state here. So explicitly in terms of the occupancy states, it's just this state. So now by tracing over the degrees of freedom in the depletion, we obtain the reduced density matrix describing the condensate here at rho A. And with a bit of algebra, we find that it's given by this here.
Question.
Yep.
What is the picture supposed to represent?
All right, so that's supposed to represent, it's called a Bose-Einstein condensate. So in the non-interacting limit, the particles will tend to occupy this zero momentum mode. And so you can actually see this here as we, as t goes to 0, we see that these particles tend to occupy these.
Okay, so maybe I should have rephrased my question. Label your axis. What's X, Y, and Z?
Oh, right. I believe this represents. Let's see. Yeah, I'm actually not exactly sure. It has to do with the momentum distribution. I'm not exactly sure what the axes represent, but essentially I think it means that this spike here represents the end of the zero.
Okay.
So you said the right word. It's just it's a histogram of px and py, basically. So you have a trap of atoms, and then you release them, and you can measure the momenta or the velocity, basically. So you think of this as just a histogram of all possible momenta or velocities, and so you get this peak at basically zero momentum, and that's the condensate forming.
Okay, and so the mixtures change as t decreases, right?
Yeah, so t is decreasing to the right,
Okay.
or maybe those are on actually either side. No, I guess t is decreasing to the right, and then maybe you can think of like px and py, because they project onto one axis, right? So they have a camera that's basically looking, so they project the velocities onto a plane, essentially.
Okay, so notice that the reduced density matrix is diagonal. So this is diagonal. And is also mixed, so it's a combination of these states here. So that tells us that we have this condensate depletion entanglement. So now we can compute the von Neumann entropy by this formula here, and after a bit of work we find that it's given by this here, where the PIs are just given by this expression here. So this looks a lot like the Shannon entropy from classical information theory. Really all the von Neumann entropy is just an extension of the Shannon entropy to quantum mechanics. It's able to quantify this information share between subsystems. So we can further generalize the von Neumann entropy using the Rényi entropy. So this alpha here is called the order of the Rényi entropy. And it's useful just because there's no universal way of defining entropy. So this gives us sort of the freedom in defining in how we define our entropy. And in the limit that alpha approaches 1, we just get back to the von Neumann entropy. We can show this using also the condensate fraction here is essentially, or is represented here by this matrix element, which is just the expectation value of the occupancies in the condensate, so divided by the total number of particles. So in the zero interacting limit, we expect to see that all particles occupy the condensate, and this fraction goes to 1. And furthermore, this can be accessed experimentally in simulations. Alright, so for my results, for a variety of systems, I computed the energies, and we have this beta ansatz, which is the exact solution to compare these energies to. It's just a test of the validity of the Lanchos algorithm in this context. Then I calculated the von Neumann and Rényi entropies, as well as the condensate fractions. And it's important to see how what kind of errors we introduce when we truncate the Hilbert space with the node cutoff. And since we're limited to only smaller system sizes, we want to see how this behavior scales in the system size. Okay, so these first plots show energies calculated through exact diagonalization. It's kind of tough to see, but what I'm plotting here is energy as a function of the interaction strength for different mode cutoffs, as well as the exact solution for the beta ansatz, just given by this dashed line here. And it's a little bit tough to see, but with increasing cutoff, we see convergence to this exact solution for all cases here. So we can only study smaller cutoffs for these larger system sizes, so 16, but we still see this convergence, especially in the small chain. So next I calculated the von Neumann entropies. So again, we see convergence in the cutoffs in each case. But we don't have a test or an exact solution to compare these results to. So what we do instead we have to see how the entropy scales in the cutoff. So we can use what's called fractional error scaling between the entropies calculated with different cutoffs as an estimate of this convergence, and also to give us a regime of interaction strings, so a regime of G's, in which we can confidently talk about these entanglement entropy. So here are some of the scaling plots. So on the y-axis we have fractional error calculated between successive mode cutoffs. So for n equals 2, we can see convergence to well under 1% for all the interaction strings plotted here, telling us that we can study a broad range of interactions for this small system size. Same thing for n equals 4. Here we see sort of this exponential convergence in the cutoff. For n equals 8 here, we don't see convergence until we hit the maximum accessible cutoff, like down here. So we're more limited as to the range of interactions we can study. And then for n equals 16, because we're limited to such small cutoffs, we don't see convergence for the interaction strings here. So we're limited, and we really would just need more higher cutoffs to study these larger systems with accuracy.
And can I ask?
Sure.
Again, I mean, I understand you have limited time, but I was trying to again understand what is changing from one figure to another. I'm trying cannot see it.
Oh, sorry.
I mean, I see that cutoff. I mean, there's different, right?
Right.
But what else?
System size. So n equals 2, n equals 4.
Ah, okay.
Yeah, sorry, it's a bit
Okay.
tough to see. But yeah. Okay, so this plot is intended to show the scaling and the system size of the von Neumann entity. So, I mean, it's tough to see kind of a clear scaling behavior, but and to see better scaling behavior, we need larger system sizes and higher cutoffs. But you can still see sort of this behavior here. And these uncertainties are calculated using the entropys calculating the max cutoff and the max cutoff minus 1. So these are important plots because we don't have a way of accessing these larger system sizes. So these are really the only ways of estimating what the behavior will look like at larger system sizes. Right, so here are plots of the Rainey entropys for different system sizes. So we see a couple of important features in these plots. First of all, we see this order in the, we see this hierarchy in the order of the Rainey entropys. So it's predicted that, or it's a fact that the Rainey entities have this sort of ordering here. So alpha equals 1 is the von Neumann entropy, and then successive alphas are always less than the previous alpha. And so here we plot the condensate fractions. So first of all, we see some expected results when the interaction is 0. The condensate fraction is 1, meaning all particles occupy the condensate, so they form, it's called the Bose-Einstein condensate. And then as we slowly increase the interaction, we see that these particles tend to get kicked out of the condensate and into the diffusion. And as that happens, the entanglement between these modes is increased. Okay, so just to summarize what I've done, so I computed the energies, the entanglement entropies, and condensate fractions using exact diagonalization. These quantities are tough to calculate using other methods, so this is really the best method to do it, especially considering the von Neumann entropies and the Rainey entropies of various orders. It's very straightforward to calculate. So we found a regime of interaction strengths in which we can confidently talk about these von Neumann entropies, just using the mode scaling and increment entropy. And then this finite size scaling plot was used to show the dependence of the von Neumann entropy on the system size. And they're important because they tell us, because we have no other way of accessing these large system sizes, just because of the memory requirements that they require. So, like I said, exact diagonalization gives us this important insight into quantities that are difficult to access via other methods, despite these limitations. So I picture this project as kind of incomplete at the moment because this method of exact diagonalization allows us to study much more general interactions. It doesn't have to be delta function interactions. So we can implement, say, Gaussian, helium-4 Leonard-Jones potential, etc. And to do that, we compute when we transition from first to second quantized notation. We compute essentially a Fourier transform of the interaction. So that would be the next step in this project, is to study these more general interactions. And then for better performance, memory-wise, it might be a good idea to transition to C++, and then just work on optimizing the code for that, so that we can study these larger system sizes with larger cutoffs. All right, so I'd just like to thank, first of all, Dr. Chris Herman, who's now a postdoc at the University of Waterloo. He really helped me through a lot of this process, and he taught me basically the fundamentals of second quantization, entanglement, and spin control. And then Dr. Adrian Delmastro, who gave me the opportunity to work on this project beginning of last year. It's been a huge help through this entire process. And then I'd also like to thank the Condensed Matter Theory group and just my friends and colleagues here for helping me through this process. All right,
Big questions from the general audience, Josh?
Can you go back to the interesting quantity slide, please?
Sure.
That was confusing. Okay, but yeah. For S of alpha, you said when alpha equals 1, you get back S of the n. Is that?
In the limit, yeah.
I'm confused how you get that.
So you have a 0 over 0 case because the probabilities are really sum to 1. So when alpha equals 1, you're taking the log of 1, which is 0. So you can use L'Hopital's.
Oh, I see. Okay, I see.
Okay.
How does the memory scale with the system size?
So it depends on what you're looking at, whether it's scaling the cutoff or the system size. But for the system size, it's I think it was exponential, the system size. So for n equals 32 and a cutoff of 3, we have the dimension of the Hilbert space is about 2.5 million. So our matrix is huge.
How much memory did they use?
Several gigabytes for that system size. So, and we need more to even diagonalize it. So
At the beginning, when you were talking about entanglement in general, did you say that information is transferred between entangled particles?
yeah, it's shared. So an example that I like to use, imagine you have two spins in the Bell state here. So in this state right here, if we measure the spins of the individual particles, we find that half of the time we get up, half of the time we get down. So, but if we measure the joint outcomes, we find that the measurements were correlated. So actually 50% of the time we measure up down and the other 50% down up. So the fact that we can't piece together the joint outcomes from the individual measurements tells us that there's this good information contained in the system.
So does that mean that if I've only heard of quantum entanglement a little bit before, if you collapsed one of the states or figured out one of them,
Right.
Is that technically information transfer faster than the speed of light?
No. Well, it's so in order to so when one observer makes a measurement and another observer makes a measurement, they have to compare what their measurements were. So they actually have to come together and say, well, I measured up and the other guy measured down.
Oh, I see.
So there's no actual information being transferred faster than the speed of light. So
need to go back to the previous slide. No. For the one when Jasper's question. One with two summations.
so?
Back, no. Further back. Is it
Back or?
I think
back?
Where Josh was asking
When the
questions.
judge asked the question,
The other way. Go forward, yeah.
which way?
It's interesting.
Forward.
Yeah, it's interesting quantity slide.
Yeah, okay. So there are two summations. The capital N is the total number of particles,
Yeah.
I assume. Now the other summation is vector little n.
Okay, yes.
What are they?
So this is just a label of a particular occupancy configuration. So when you're doing your computations, you have to define an ordering of these occupancy states. So the first state would be n, 0, 0, and so on. That might be labeled, that's one possible configuration of this n. So it's just a sum over all possible configurations.
Configuration.
Yeah.
Thank you.
Two kind of related questions. How close are you to the experimental realization of this? Can they actually do n equals 16 systems, or?
Yeah, so as far as I know, the Lieb-Liniger model has been implemented. I'm not exactly sure how many particles they've
Like a
used.
Bose-Einstein condensate is still hundreds and hundreds of particles.
Right.
So,
Yeah, so off the top of my head, I'm not sure how many particles they looked at, but
fair enough.
it has been implemented experimentally in optical.
And then related, do you have a method of going to finite temperatures with this, or does that tank everything?
So we can calculate excited states in this method. I'm not sure how the model would change off the top of my head, but yeah, I think it is possible.
Some questions over there?
Are the exact like energies and entropies like necessary for your results, or are the ratios?
So the ratio between
Like the different energies. Or different energies, whatever. It's a lot easier to calculate the ratios like between the IPCs than it is to calculate the IPCs themselves. So, like there are ways to estimate it. Like if you look at like the analytical hierarchy process, they talk about ways to estimate the ratios between those values, not the values themselves. So I don't know, is it like the exact values necessary in like what you're doing here? Or?
I don't know enough about the method you just said, but yeah, so I mean these are the exact values,
Right.
so I mean that's important in its own right. So yeah.
Russ?
I had a follow-up on the previous question. So apparently I misunderstood some of your talk. So I thought that you were looking at temperatures which are close to zero, but not exactly zero. Because if they are exactly zero, where do you get states with m not equal zero from? I mean, they should not be. I mean, they should not be there. Right? I mean, according to the occupancy should be zero.
So
Of those
as
states.
soon as we turn on interactions, we'll get, because the m labels the momentum, not the energy, essentially. So as soon as we turn on these interactions, we'll see these particles tend to be kicked out of the condensate.
Okay, so even though the total energy is zero, or the energy of each state is zero, then. Okay.
In the non-interacting case.
Yeah, the energy's not zero.
I see.
Other questions? Okay, if not, let's thank Dan again.